friends, I am Vijay Shankar Dwivedi, TA in this course. In this week, in previous lectures, you have studied about the directional stability, directional control, lateral stability and the lateral control. You have studied the stability derivatives CL beta and Cn beta, and the control derivatives Cn delta r, Cn delta a and Cl delta r and Cl delta a. We have seen for the stability we need the positive value of Cn beta and negative value of Cl beta. If we see in a conventional design, this is our aircraft. For the positive value of beta, we can see this surface will feel a force outward in this board and this will give a positive yawing moment. So, the Cn beta will be positive, or the contribution of this vertical tail is positive toward the Cn beta. And if you see for the Cl beta, when we have the positive value of beta, there will be a force outward this board, and suppose this is the aerodynamic center of this vertical stabilizer and this is the body x axis. So, there will be a rolling moment because of this arm. For the positive value of beta, this roll will be negative. So, we can say the contribution of this vertical tail is negative towards the Cl beta. And for the control derivatives, suppose this is our rudder. If we deflect this rudder with some positive value, there will be a force inward this board and this will give a negative yawing moment. So, Cn delta r will be negative, and for the positive deflection of the rudder, the roll generated due to this extra force will be positive. So, the value of Cl delta r is greater than 0, and when we deflect the aileron with positive value, means right aileron up and left aileron down, there will be a positive roll. So, we can say the Cl delta a is greater than 0. And next control derivative Cn delta a. For the positive deflection of aileron, means right aileron up and left aileron down. If I see the front view, this is the front view. Right aileron up and left aileron down. In this case, this wing will feel the more lift, and as you know, the CD is equal to CD naught plus KCl square, and here you can see the CD is increasing with the square value of the Cl, means if the lift increases on the right wing, this will significantly increase the value of drag and this will give a yawing moment. If I see the top view of the aircraft, on this wing there is more drag and this will try to yaw the aircraft with some negative magnitude, and that is why for the positive deflection of aileron we are getting negative value of yaw. So, C n delta A will be negative. Let us solve one problem for a closure loop of these derivatives. For a conventional design, the vertical tail contribution for the CL beta is minus 0.0029 per degree. The Cn beta is 0.0018 per degree. Cn delta R is minus 0.001 per degree, and the CL delta R is 0.0002 per degree, and the wing and the fuselage contribution for the Cn beta wing and fuselage is minus 0.0008 per degree, and the contribution of wing and fuselage towards the CL beta is 0. So, what will be these variables for the aircraft? Let us find. This is the design. Suppose this is the CG. The aerodynamic center of the vertical tail is somewhere here. This is the body x-axis. Now, this is the rudder. What will be the value of CL beta for this design? We can see the contribution of the CL beta of the vertical tail is minus 0.0029 per degree, and the wing and fuselage contribution to the CL beta is 0. So, the net value of for this aircraft, the CL beta will be minus 0.0029 per degree. What will be the value of Cn beta? The contribution of wing and fuselage to the Cn beta is minus 0.008 per degree, and do not get confused with this minus sign, because if our CG is located in such a way, if we have only wing and fuselage, and about this axis, this z axis, this portion is creating more moment than this portion. In that case, this will be negative, because the positive beta, this will generate a negative yawing moment. That is why this Cn beta wing and fuselage is this, but after installing the vertical tail, our net value will become positive, and that is our requirement for the stability. Means the vertical tail is providing us the directional stability. So, what will be the value of the Cn beta for this configuration? We have to add it this simply. Wing and fuselage contribution is minus 0.008, and the vertical tail contribution is 0.0018. So, net will be 0.001 per degree. Now, coming to the Cn delta R. The contribution of the wing and fuselage is 0. The Cn delta R is minus 0.001, and this will remain as it is. So, this will be minus 0.001 per degree. Coming to the CL delta R, the rolling coefficient derivative with respect to the rudder deflection. CL delta R is given to us is the 0.002. So, this will remain as it is. .0002 per degree. Now, the question is, if the designer installs one more vertical tail at this position, these both vertical tails are identical and their moment arm from the CG, the yawing moment arm is same for both the tails, and the rolling arm, suppose the aerodynamic center for this tail is somewhere here and this one is somewhere here, these are also same. So, what will be the derivatives for this design? Let us see. The CL beta, when we had only one tail, for the positive side slip angle, it has a tendency to roll the aircraft with some negative value. Now, for the positive beta, this surface will try to roll with some positive value, and both are identical. So, both will nullify each other, and the resultant value of the CL beta for this aircraft will be 0, because there is no contribution of the wing and fuselage, this is 0. Now, what will be the value of Cn beta for this configuration? For the positive side slip angle, this surface has a tendency to provide a positive yaw. This also will feel a force to outward this board, and that will also try to give a positive yaw, and both are identical. This yawing arm is also same. So, the contribution of this will be added to this aircraft into this. The vertical tail contribution of the Cn beta is 0.0018, and of this design it is 0001. So, net will become 0.0028 per degree. Now, coming to the Cn delta R, suppose this is the rudder, in this surface also there is a rudder, and the sign convention is same for both the rudders. If you give a positive deflection into the rudder, this will try to give a negative yawing moment, this also will try to give a negative yawing moment, because for the positive deflection this will also feel a force inward to this board, and that will give a negative yawing moment. So, net will be doubled, and this will become minus 0.002 per degree. Now, coming to the CL delta R, for the positive deflection of the rudder, if this is the aerodynamic center, we can assume a force will be applied at this point, and because of this moment arm, it will have a tendency of the positive roll, and for this surface, the force, the direction of the force will be similar for the positive deflection of rudder, but this will give a negative roll. So, net will be 0. Now, coming to the next part of this question, the designer here has installed this is our original design, and now the designer has put one more vertical surface at this position. The moment arm for this, suppose this is the aerodynamic center of this one, and for this the aerodynamic center is here. For the both, the moment arm is same, suppose the CG is somewhere here. So, what will be the values of this derivative? Coming to the CL beta, due to this surface it was minus 0.0029. For the positive beta, this surface also will have a tendency of the negative roll. So, both will be added up. This arm is same for the both surfaces. So, the magnitude of moment will also be same, and the net will be added, and this will become minus 0.0058 per degree. Now, Cn beta for the positive side slip, this will have a tendency for a positive yaw, and this surface will have a tendency of the negative yaw with the similar magnitude, because the arm length is same. So, the net will be wing and fuselage contribution, and wing and fuselage contribution for the Cn beta is minus 0.0008. So, this will become minus 0.0008 per degree. Coming to the Cn delta r, for the positive deflection of the rudder, this surface had a tendency for negative yaw, and this surface will have a tendency for the positive yaw, and this moment arm is same for both the surfaces. So, their net will become 0. So, this derivative will become 0 for this configuration. Now, what will be the Cl delta r? For the positive deflection, this surface has a tendency for the positive roll, and this also will have a tendency of the positive roll. For the positive deflection, the force applied here will be inward in this board, and this will try a positive roll, and this will become 0.0004 per degree. And the last part of this question is, now the designer has installed one vertical surface here, and the moment arm for this and the moment arm for this tail is similar, and the rolling moment arm is also same. So, for this configuration, the Cl beta, due to this vertical tail, it has a tendency of the negative roll for the positive beta, and for the positive beta for this surface it will have a tendency of the positive roll. So, net will become 0, because both has the equal moment arm for the roll. And the Cn beta for the conventional diagram we have 0.001, and for the positive beta, this will have a tendency of the negative yaw, and the magnitude will be minus 0.0018 per degree. So, the net will become minus 0.0008 per degree. And the Cn delta r for the positive deflection of the rudder, this rudder it has a tendency of the negative yaw, and for the positive deflection of this rudder it will have a tendency of the positive yaw, and the net will become 0, because this moment arm is same. Now, the Cl delta r for the positive deflection of the rudder, this surface has tendency of the positive roll, this will have a tendency of the negative roll. So, the net rolling moment coefficient will become 0. So, coming to the next problem, an aircraft has vertical tail having a symmetrical airfoil NACA 0010. With lift curve slope of airfoil (0.09 per degree), and the vertical stabilizer area is 12 meter square, and the rudder area is 3 meter square, and the span of the vertical tail is 4 meter, and this aerodynamic center of the vertical tail from the CG of the aircraft is 6 meter, and we are given the wing area is 50 meter square, and the mean aerodynamic chord is 3 meter, and the wing span is 15 meter, and the dynamic pressure at the tail is the free stream dynamic pressure, and the span efficiency factor is 0.95, and we are given with this plot. This is SR by SV, and this is tau. .2, 0.4, 0.6, and over. This is 0.15, 0.25, this is 0.35, 0.45, and so on. We have to find the rudder control power. What is the rudder control power? This is nothing but the Cn delta R. We can write the yawing moment due to change in the rudder deflection. For the positive deflection, we will have a negative yawing moment. So, we can write minus dym because this is the change in the deflection, and this will be the force on this vertical tail multiplied by this moment arm. So, this we can write the area of tail, that is SV, and we need the lift coefficient of this vertical tail, and we have the 2D lift coefficient. Now, we will have to convert it into 3D lift coefficient, and we know this is given by, suppose A is the 3D lift coefficient, then we can write it A naught by 1 plus A naught by pi aspect ratio into E. This is A naught. And if you substitute these values, this will be 0.09 divided by 1 plus 0.09 by pi, and aspect ratio of this surface, the span square divided by area, span is 4. So, we can write aspect ratio, span is 4 meter. So, 4 square by 12, and this will be 1.33, and E is equal to 0.95. And keep in the mind, this we always write in radians, and this is in per degree, we have to write in per radian. So, we will have to multiply it by 57.3. The unit of this will be unit of this, and this will be always in radians. And by solving this, we will get the 3D lift coefficient of the vertical tail, and this is 0.04. Now, let me erase this part. This is A. So, the lift coefficient, and now we need to multiply this with the angle also, and as we know, the tau is d beta by d delta r. The change in angle of attack observed at this vertical tail with per unit change in rudder deflection. For our vertical tail, this SR by SV, you can write it 3 by 12, and this is 0.25, and corresponding to 0.25, we have the value of tau 0.4, and from here we can find d beta, and this is tau into d delta r. So, I can write it the angle as tau d delta r, and because this is the moment, so I need to multiply it with this arm length, and this is, suppose I write it with the LT, and this is 6 meters. Now, to find the yawing moment coefficient, I need to divide this by half rho v square, wing area and wing span, and then I will get minus d Cn half rho v square S into B, and this will be cancelled, and now we are left with minus dCn is equal to SV into A into tau d delta r LT divided by S into B. And now, if I bring this d delta r to the left side, so I have minus dCn by d delta r is equal to Sv into A into tau into Lt divided by S into B. And now, if I substitute these values, Sv is the area of vertical tail and this is 12 meter square. The 3D lift coefficient we calculate 0.04. The tau we got it 0.4 corresponding to 0.25 SR by Sv. And Lt, this is 6 meters, and divided by the wing area, this is 50 meters square, multiplied by the wing span, that is 15 meter. And by solving this, we will get the value of minus dCn by d delta r, and this will be 0.001536 per degree. And dCn by d delta r is nothing but the Cn delta r, and this will be minus 0.001536 per degree. Coming to our next numerical, an aircraft has directional stability Cn beta is equal to 0.002 per degree, and the rudder control power Cn delta r is minus 0.0015 per degree, and the maximum allowable rudder deflection is plus minus 30 degree. We have to find the maximum crosswind velocity that can be handled during landing, and we are given with the weight of the aircraft, the 5000 kg, the wing area S 50 meter square, the CL during the landing is 1.5, and at the sea level the density of air is 1.2 kg per meter cube. Now, we have to find the maximum allowable crosswind that can be handled during landing. Suppose this is the top view of the aircraft. Due to the crosswind, here will be beta, and due to beta there will be one force acting on this vertical stabilizer in this direction, and for the landing we will have to balance this force by deflecting the rudder. And now, suppose the beta is positive, in that case we will deflect the rudder in this direction. Now, we have to find the maximum allowable crosswind speed, and for the maximum speed we will have to deflect with the maximum amount. So, we have to deflect this rudder with the 30 degrees. This is the maximum allowable rudder deflection given to us. Now, during the equilibrium, due to the rudder deflection, the force will be acting in this direction, and this force will be acting in this direction, and we have to balance the moment about CG at the time of landing. So, both moments must cancel each other, or we can say the algebraic sum of the both moments will be 0. So, we can write Cn beta into beta plus Cn delta r into delta r is equal to 0. Do not get confused with this positive sign, because this Cn delta r is already negative. So, this is taken care of, and from here I can write the beta is equal to minus Cn delta r into delta r divided by Cn beta, and if I substitute these values in this equation, I will get beta is equal to 22.5 degree. Now, we have this beta, and as we know we are given with the CL and the weight of the aircraft. From here you can find this forward speed. Suppose if I write this with the u, I can find u from here, and if I have the beta and u, I can find the crosswind velocity, the maximum crosswind velocity also. So, now let me calculate the value of this forward speed u, and I can write u is equal to root over w by half rho s CL during the landing, and if I substitute these values, 5000 into 9.8 gravitational constant, half rho is given to us 1.2 kg per meter cube, the area is 50 meter square, and the CL is 1.5. And from here I will get the value of u is equal to 33 meter per second. So, now I have this u 33 meter per second and beta 22 degree. From this u and this beta, I can find this velocity, the resultant velocity of the crosswind and this forward speed, and we know this u is, if I write this with the capital V, so u is the V cos of beta, and from here V is u by cos beta, and the maximum crosswind speed will be V sin beta. So, I can write, and I write this with the small v, I can write V is equal to capital V and sin beta, and this will be u by cos beta into sin beta, and this will be u tan beta, and if I substitute these values into this, this will be, the u is 33 meter per second and beta is 22. So, tan 22 degrees, this will give us the value of maximum crosswind that can be handled with the rudder, and that will be 13.66 meter per second. So, now we have the maximum crosswind speed that we can handle with this rudder during landing, that is 13.66 meter per second. Now, here you can observe the beta is minus Cn delta r into delta r by Cn beta, and you can see if I increase this Cn beta, means my aircraft becomes more stable. In that case, I will have to, either I will have to improve this Cn delta r, or you can say the rudder control power, or you will have to deflect the rudder with the more amount. So, the message is, if your aircraft is more stable, means higher the value of Cn beta, the pilot will require more effort to fly the aircraft. Thank you.